So good afternoon. Welcome to this webinar on the fire performance of FRPs hosted by Composites UK. I'm Stella Jobe, Sustainability Manager for Composites UK, and I'm facilitating this afternoon. Our speaker today is Nigel Keen, who is an independent consultant with his own business, Creative Composite Connections. We are recording the webinar, so you will receive a copy of this or a link to a copy of this and a PDF of the slides within the next day or so. And we'll also include a copy of the Fire Performance Good Practice Guide, which was produced through Composites UK last year, published about last September, I believe, for which Nigel was a contributing author, as was I, in fact. If you've any questions, please type these in the Q&A box, which is at the bottom of your Zoom screen, rather than the chat. So if you can put your questions in the Q&A box. So you can put in a question whenever you like as Nigel's speaking, and we'll address them at the end after about probably about 2:45 when Nigel finishes the presentation. Then we'll address the questions and we'll aim to be finished at 3 o'clock. So with that, I will hand over to Nigel to begin the presentation.
Thank you, Stella, and welcome everybody. Really just to set the scope for this, I'm going to essentially use a lot of the information and try to talk you through fire in composites and base it on, if you like, the good practice guide that we put together last year. So we'll be, sorry, there we go. So I'm going to have a quick talk about composites in fire scenarios. Some of the language that's used, which can be very confusing. We're going to talk about combining materials. So composites, as you know, are a number of different materials all put together to get the best out of combined materials, but also they're also part of assemblies, and that's important. We'll talk very fleetingly about modeling prediction. We'll go into fire a little bit, talk about the fire triangle and different ways to stop fire, and that will lead us on to the fire smoke toxicity toolbox that's available to composite formulators. So how would we improve fire performance? To which strategy should we use to stop fire? Then we're going to run through the different sectors and the standards and tests involved in those. Now that's a huge topic which I can't really do justice to in 40 minutes, and it's covered in quite a lot of detail in the guide. So I'll go through some of the main outlines of each sector, some of the trends there, and then we'll talk about the future. What are the new markets and opportunities? Where do we see fire performance or composites that have fire performance going to in the future? And obviously we've got a link back to the Composites in Fire Good Practice Guide, and then I'll finally finish off with my Q&A. So composites, especially FRP, organic matrix composites, they're plastics, aren't they? They don't burn. This is something that is a wide misconception, and certainly at the moment where composite, the word composite is used very loosely for all sorts of things, including Glenfield cladding, which isn't FRP, then we have a lot of challenges around the terminology. But what I would say is composites are used very widely in an awful lot of applications where fire safety is a requirement. So, they're used, they might burn, they might not burn. They are certainly not always non-combustible, which is a word that is bandied about quite a lot. But they can be limited combustibility. And the fact that they burn need not necessarily be a problem in a fire safety scenario. And in fact, you might want to use composites as a sacrificial layer or a barrier layer, and they work very well in those kind of applications. So composites, we have a huge amount of materials we can choose from to put into a composite. We've got a lot of different places where you can deploy those materials, and a very big formulation toolbox that means we can put additives, different layers into our composite, and provide a solution for a lot of different fire scenarios. So you know, one of the picture I have here is a set of shielding for a jet fire. So we try to protect a sort of a sensitive structure, something maybe containing flammable liquids from a jet fire that might be impinging on it. And the solution that was found for doing that effectively was not a non-combustible solution, but more of a protective solution. So finding something that will resist jet fire has led us to some very fire-resistant composites that would meet those tests. So as I say, it might not be incombustible, but we can actually use them to protect structures that might be non-flammable materials from fire and heat. So understanding what's required is really important. So understanding that mix of language is critical. So you've got to decide what your composite part or component needs to do in its normal function, and what sort of service conditions or test regimes it might have to survive. What are the standards and specifications governing that? What are the failure consequences? If something does burn, if it does fail under fire, what are the risks? What are the real risks? What's the risks to life? And that will determine a little bit what fire strategy, fire smoke and toxicity strategy you should go for, and it will affect which strategy you go for in terms of how much filler, what sort of glass or non-combustible materials you use, what sort of layering you use will affect your design, may affect some of the other performance criteria such as weathering or stiffness or strength or weight. So what are your, and also you need to decide what your cost constraints are against competing materials. Composites won't necessarily, and quite often aren't necessarily the cheapest option, but they may be the best compromise of weight, performance and fire resistance, and often are. So when we talk about reaction to fire, these are some of the characteristics we're looking for. So if we're talking about preventing fire growth, non-combustible materials are great if they won't actually sustain a flame. If you can attempt to burn them, but they just won't burn, that's useful. They may not have anything burnable within the material, being non-combustible. Ignitability, how easy is it to actually sort of get a flame or get them to burn? Once they're burning, how much do they contribute fuel to the fire? And how fast does the fire grow, and if there's any exothermic reaction that helps release heat and fuel the fire and help the fire grow. So, and flame spread, if you have a small fire in one corner of a room, how fast does that spread across that wall or across to other materials? So surface flammability and fire spread are very important. And we also have the situation, particularly with thermoplastics and reinforced thermoplastics, if the materials start to melt, you might get drips and drops or that also spread the flame vertically. So flaming droplets, for instance, was a major issue where thermoplastic materials still alight can drip and spread the flame that way. Finally, smoke and toxicities is very important. So if you have an enclosed space, smoke, particularly toxic smoke, is probably the biggest killer in a fire. It obscures vision, it stops people escaping properly, and ultimately it's probably what stops you breathing, even if and that's more likely to cause death than actually someone being burnt, because they'll tend to run away from the heat. And in terms of, that's reaction to fire, but the other sort of criteria is fire resistance. So fire resistance is about containment of fire. So it's about stopping a flame from burning through something. It's from keeping the structure that's made of your composite material intact and functional. So if it's supporting the floor above, it doesn't collapse. It's keeping the heat within the fire site. So if you've got a fire in one room, you don't want it to spread to the next. So thermally insulating it. And you also need to understand at what temperature your composite starts to failed in its structural capabilities. And load bearing may not just be sort of how much weight something will bear or the stiffness that if it starts to sag or creep, but it could be additional loads such as impact, vibration, and blast. So those kind of additional things that can break the integrity or alongside the fire and cause a failure. So all of those things can be tested, all of those things can be measured, and there are test regimes and standards built around all of that kind of testing. So composite materials, as I said, we've got an awful lot of options. So you can put your fire resistance into almost any aspect of the composite material. You can put it on the surface. So if you're talking about maybe a low intensity flame or a cigarette, you may want something that's simply self-extinguishing, that's not going to set light simply because it's in contact with a burning ember or a small naked flame. And that can be done simply by a very thin coating on the surface often. You can put that paint into the mold and have that as a fire resistant gel coat. You can put it into a surface veil and actually have a layer immediately beneath your surface that is fire resistant and protects, if you like, a structural laminate or something underneath. You can actually build slightly thicker layers and you can decide, okay, I can usefully sacrifice, say, a third of my composite and still have enough structure to hold something up. So we'll build in extra layers and we'll model the amount and speed that we burn the composite away, and we allow perhaps the glass to hang and provide the thing. So you can actually have sacrificial layers that will protect the structure and keep it functional for a period, allowing escape. Core materials themselves are good insulators. So composites are good insulators of themselves, but core materials being very lightweight and having can be very good at insulation, so they can be a part of the solution. And fillers can be used within the matrix to reduce your combustible content. And often we're using inorganic reinforcing fibers rather than thermoplastic or carbonaceous ones, and they can be essentially fire resistant. So the more glass, for instance, you've got in a product, the higher glass content, the less likely you've got the less organic matrix you have to burn. Finally, you can actually fully modify your material, so you can have a resin system that is inherently fire safe, that produces a lot of char that's very difficult to ignite or burn, or you can modify it in some way. You can add additives, you can really play with the matrix system to help you with fire. And finally, when you're talking about combining materials, you have to look at the whole system. So you have to look at where you're using it. So if you've got a composite component and it's fixed with metal fixings that might provide a heat path through or around it, or it may warp or move away from another component from a different material and provide a gap that allows flame to pass, then you have to look at those challenges as well. So fixings, assembly, sealing of your penetrations, looking at gaps and things like that is important. So you have to consider all of these things when you're talking about what your fire resistant composite's got to do. So we talk about fire progression and the combustion products briefly. So first thing that happens with a fire, something exposed to a flame, is it will tend to heat up. And generally speaking, if it's a organic containing material, that will tend to vaporize or pyrolyze some material, so that some of the organics will become vapor, and some of those vapors may be ignitable. So that then creates your flame, your burning. As things burn, they'll tend to either turn to char, they may give off smoke, they will create ash. And as the flame progresses, you'll end up with a heating zone as it passes through the laminate. You may get melting and dripping. So basically, you've got a progressive burn through a product, if you're talking about burn through. And all these different products, fire products, can come away from it. And you have to manage all of those if you're going to create a successfully fire-resistant composite. So we talked about fire and ways to stop fire. So you've got a number of different strategies that we can use to actually sort of stop fire in its tracks. Now, obviously, fire needs three things. It needs fuel, usually organic materials are the best sort of things that burn. So anything that's oily, anything that's petrochemically derived, generally speaking, it will burn. You need energy, so you need some heat. If you've got no heat, if things aren't hot enough to volatilize, they tend not to burn. And you need oxygen for the fire reaction itself. And so those three things, fuel, energy, and oxygen, are the prerequisites for fire. So we can do several things when we're building our composites. We can reduce or eliminate anything that's combustible. So we can reduce the resin content, if it's an organic resin. We can go to, we can get rid of any thermoplastic fibers that might be flammable. We can perhaps remove natural fibers or something else that's flammable. So we can get rid of the combustibles and perhaps substitute them with other things. So high glass contents, inorganic fillers, and keep the combustibles to an absolute minimum. The other way we can do this is to prevent heat from reaching the fuel. So we can reflect or cool or insulate the fuel source from the heat. So if we've got a barrier system or a foil on the surface or something that's reflective or insulating, then we can actually sort of create a barrier between the heat and the fuel. So in some cases, this could be a veil. Sometimes we even use things like metal flakes in a coating to provide some reflective properties. We can cool, quench, or trap the heat. So if we can use high heat capacity materials or materials that will give off water as they decompose, so things like aluminium hydrates will actually decompose when they get to sort of 180 degrees, 200 degrees. So before everything really starts to take off, you're actually sort of quenching the heat by sort of providing water that will vaporize the steam. You can actually sort of generate and smother the oxygen. So if you can drive the oxygen away from the fire by creating other gases, like could be nitrogen, could be carbon dioxide, so something that a non-flammable gas, then you can actually sort of drive the oxygen away from the fuel source and stop that happening. And finally, you can create sort of other barriers. So you can create an incombustible barrier. You might be able to get something to inch-mess, create a nice glassy shield and seal off the unburnt laminate from the air. And finally, we can stop the fire chemistry. So we can actually sort of suppress the flame by actually putting chemically reactive agents into the vapors and actually snuff out that exothermic reaction that requires the free radicals. So we can put things like bromine and chlorine gases into the or free radicals into the gas, and that will soak up the OH and oxygen free radicals that are part of the fire chemistry. So they can actually sort of snuff out the fire quite easily. So we've got, in our toolbox, we've got a whole number of different things. We can go non-combustible. So we can look at, so non-combustible composites might be things like ceramic matrix composites or metal matrix composites. We can use sort of quite brittle matrices. We can use cement and have a basalt system, for instance, or or glass system. So we can actually create composites where the matrix is quite brittle and the fibers may be providing toughness or impact resistance. And we can create non-combustible composites in that way. So composites can have very low organic content, and we can actually create or minimum organic content, and you can actually pass some non-combustibility tests doing that. The next stage really is to, as I said, minimize the organic content, put lots of filler in. So fillers are very useful for fire, smoke and toxicity. They reduce the amount of stuff that is there to burn. So simply having a high amount of inert filler in your system will be helpful. The drawback is, of course, that you can't then have a high fiber content because you need the resin matrix to wet the filler as well as the fiber. So your fiber content will drop, which may not be a problem if you want, for certain applications, so things like worktops, things like where you've got something that's fairly thick and stiff, and that's its primary purpose. It's not too much of a problem to have a lot of filler in there. But if you want something that's stiff from a point of view of tensile loads and impact loads, then you quite often want more filler, more fiber. So in that situation, high field systems can be relatively weak. So all of these things can be used. So when you're talking about fillers, then the hydrated mineral fillers are really good as well. So hydrated mineral fillers will be things like aluminium hydrate, releasing water of hydration at certain temperatures. If you've got a process that needs higher processing temperatures, then you might use magnesium hydrate, which doesn't start to decompose to sort of 250 plus centigrade. And other fillers will be multi-purpose, so catalytic fillers. So things like the antimony oxides, other metal oxides, do more than one thing. They can be inert themselves or non-flammable themselves. They can release non-flammable gases, and they can also act as catalysts to promote some of the other sort of chemistries. So they can actually be useful with bromine, for instance, to increase the effectiveness of some of those some of those other additives. So when we're talking about the matrix systems and the additive systems, then certain chemistries lend themselves very well in fire. So typically resins that are fire resistant have got a very high aromatic content. So it means that when they burn, they tend to form quite solid char. They have a high char content. So the carbons in the organic structure form into ring structures. They produce graphitic structures that themselves are quite fire resistant. So phenolics are very difficult to ignite. They might smoke a little bit and they'll form a char, and that char is actually itself fairly flame resistant. And we've seen quite a lot of other things come forward. So some of the benzoxazines, some of the furanes and fluorophore alcohols have got a similar sort of way that they resist flame, and they're being used quite widely now. Halogen systems, so brominated systems, chlorinated systems, and fluorinated systems work very well in the gas phase. So they said the free radicals, halogen free radicals, are very good at snuffing out the actual flame reaction, and they're very widely used. They have a drawback in that they can sort of potentially leach. Some of the halogen systems have proven to be carcinogenic. They're not particularly healthy. They can be persistent in the environment. So some of the products are not great. They get into the food chain, and they have been discovered in all kinds of places. In polar bears and things like that at the top of the food chain. So, if they aren't reacted properly into the resin system, they can leach, they can become an additional problem in the environment. However, they're very, very effective and save a lot of lives. So we've, for instance, we've seen with halogenated materials in things like TV surrounds and things like that, where TV fires increase where you've gone to non-halogen or gone away from fire retarded plastics, and that can be a hazard in itself. So you have to balance, if you like, using very effective fire additives and the needs of the environment. Phosphorus fire retardants can work very similarly. You tend to need a little bit more of them to carry out the same effects. So again, the phosphoric acids and things like that can actually do very well in suppressing flame chemistry. They're slightly more benign, generally speaking, in the environment than halogens. Still a little bit corrosive sometimes, and certainly halogenated products like hydrogen bromide, hydrogen chloride, they're all acids, so they're not great when you're talking about the fire products potentially having a corrosive effect or a toxic effect. So phosphorus is sort of a replacement for halogen, somewhat less effective, but somewhat more environmentally benign, and finds increasing use. Intumescence are good. We've mentioned that. So an intumescent is where you have a gas generated that produces your foam. So it tends to foam your char and expand your char. And so you provide some carbon source, you provide a blowing agent, and you create, if you like, an extra insulation layer through your char. So you have something that expands to meet the flame and insulates the unburnt material quite quickly. And they can expand quite hard. And they're used for things like seals. So if you have a gap and you want to seal that gap and prevent flame growth, then having an intumescent system adjacent to that gap can be very, very useful. And they're very good for resisting things like burn through tests. Core materials can be very good in insulation, and a lot of the traditional cores are very good for that purpose, but some of them are themselves flammable. So we've seen, sort of ordinary polyurethane foams and things, they're both flammable and very smoky. But using core materials that are less so, so PVC, for instance, is a core material. It's quite fire resistant of itself, being a chlorinated material, but it does tend to melt away and has other issues. It can smolder a little bit. Other insulation barriers and core materials will be things like Nomex foams, Nomex honeycombs, aluminium honeycombs, and syntactic cores with phenolics and glass bead, things like that. So core materials can be very insulative and very fire resistant. Some of the natural core materials like balsa and cork are also very, very good in flame, and sort of tend to char and resist fire very well. And finally, in our tool set, we've got the nano material. So that's a very broad class of additives. They tend to be, no single nano material is, if you like, the full is the full sort of wonder silver bullet, but in combination with other fire resistant parts of the system, they can buy their way into systems. So sort of clays, so that sort of montmorillonites and layered double hydroxides, so layered materials that can be reactive and promote chars are very useful. Sort of nano metal oxides are being used quite a lot, and they can be coated onto other fillers, and all of these things can tweak and improve the performance. Carbon nanotubes and graphite also look promising. So there's a whole load of nanomaterials that can be used and deposited onto other materials or put onto fibres or fabrics, and be used in clever ways to actually boost your fire performance, and sort of get you to that next level of passing the test and the next level of safety. stopped the... Hang on, I seem to have stopped my... There we go. So standards and regulations. So sadly, regulation often follows disasters. So if you look at the safety of life at sea regulations, it comes out of really the sinking of the Titanic, which some people still say was partly at least caused by a coal fire in the hold that was there for some time and perhaps weakened the structure before it was hit by the iceberg. We've had recently the Grenfell disaster, again not a composite disaster as such as we know it, an FRP one, but it's certainly encouraging government to completely look at the way that the building regulations specify fire and how people control those. Aircraft disasters are, thankfully very few, but they have, each time there is an issue, it gets the regulations re-looked at, and things like Piper Alpha have made the offshore oil and gas industry really sit up and look at what they're doing as well. So there's all of these things tend to form changes in regulation. The standards that result of those changes are often designed for traditional materials. Composites are obviously a relatively new material, and quite often the standards are not designed with composites in mind. They can be very sector specific. The standards can, if you like, prohibit the use of anything other than non-combustible materials quite often. So they're based around steel or concrete, and they don't necessarily allow for non or combustible materials to be used. And often a lot of tests are for aimed at single materials. So if it's a plastic doing a UL 94 test, it's not necessarily the same as a reinforced plastic doing that kind of thing. So that sometimes the tests don't deal well, the materials tests don't deal well with a combination of materials. So standards and regulations can be a bit of an issue if you're trying to bring a composite that's not usually in that market to a new market. So let's cover some of the markets. So in construction, then this is quite kind of one of the earliest regulated markets. There's a lot of standards and codes. Most of the construction materials and actual buildings have a test, have a regulation. They can be very large tests. It's for whole systems, whole rooms, whole buildings, as well as small tests for things like floor coverings, for wall coverings, window frames, doors, door closures. So in the UK, the BIS 476 series is widely used, but that's really been superseded a lot by the European 13501 Euro class, which is required, generally speaking, for your CE marking. So there's a whole variety of tests for construction. They range from, if you like, the reaction to fire test to the fire compartmentalisation testing. In rail, then we have a lot of challenges. Again, one of the things that caused a lot of heartache was the King's Cross fire. So a lot of stuff was looked at in terms of the interiors of stations. But rail standards recently were harmonised across Europe into EN 45545, based on different hazard levels for rolling stock. So whether a train is entering tunnels, whether it's in the open. This is based around evacuation times for the rolling stock. And London Underground have, still very stringent tests, and they have their own set of fire safety performance testing, which they've only recently amended to sort of go away from the 6853 tests and sort of allow testing under the EN 45545. So actually some interesting areas there, particularly around smoke and toxicity and some of the combustibility testing. So it's a challenge, but there's some real good progress, and actually a change of standard sometimes gives people an opportunity to improve materials and get composites specified and on board. In the marine sector, again, a lot of regulation. Some of it really stops composites from being used structurally. So for very large ocean-going vessels governed by safety of life at sea, IMO regulations, structural composites are a challenge. There's a couple of ways you can use Section 17 to try and specify and describe a vessel that you can get through IMO, but it's a real challenge to do. So generally speaking, for structural applications in marine, it's steel that is specified or non-combustible materials that are specified. But as soon as you start talking about the high-speed craft, which obviously need to be lighter weight, then there's a code specifically for those, and composites can buy their ways onto those craft. In passenger ferries, there's an EU directive that's quite prohibitive but that can also be got around a little bit. So some countries allow passenger ferries that are built to the high-speed craft code, provided they operate within the countries or the flag states' waters rather than between several different countries in EU. Inland waterways where evacuation perhaps is slightly easier. Again, there's a bit more variety, so composites can be used quite widely on inland waterway boats, with the main sort of restriction being around incombustible materials in engine compartments and things like that, where containment is very important for engine buyers. And in the yachts market, again, we have something called the Maritime Guidance Notes for smaller vessels, which cover a whole load of different testings. Composites can be used in some cases, but as you go above sort of 12 passengers, you get more restrictions. So again, there's a whole load of standards in that space. A lot of those are links to those are in the guide, and you can follow up on some of those. In the oil and gas sector, then as I said, we've got a lot of heartache was done. Fire and blast protection is one of the perhaps surprising things. So we sort of talked about ablative and intumescent materials that can resist and insulate sensitive structures from things like jet fire. So composites are getting into those situations where they're used to wrap steel or to create a barrier to fire, protecting its structures underneath. And equally, there's a lot of opportunities for lightweighting. So a lot of the stuff that's not the semi-structure, if you like, that's important, but if it's made in traditional metal materials, is heavy, then handrails, gratings, ladders, things like that are increasingly being used with phenolics and fire-resistant composites. And actually, piping, so getting weight out of structures is important for offshore as things go deeper, and the actual self-weight of traditional materials becomes really difficult to handle. Then composites are finding their way onto those applications, but they do have to meet those sort of high levels of fire performance. In automotive, the requirements are much less, but for instance, interior materials require a certain level of flame resistance against ignitability. Fuel tanks have got their own tests, and sort of increasingly now batteries are going to be one of the next areas that's going to be regulated and standardized. And I think there's some real challenges in providing sort of good containment for potential battery fires. And composites are right in the mix when it comes to finding the right lightweight solutions for battery fire containment. Again, aerospace is a massively regulated market. It tested for almost every material that might go on an aeroplane. All of the interiors need to be self-extinguishing. You have to have a low fuel load. They're quite interested in more and more interested in smoke toxicity. In cargo areas, you need containment. In engine, nacelles and things like that, you need containment. They have sort of different categorizations for the containment areas. So fire resistance is a big burner pointed at your things. It's 5 minutes to burn through. Is fire resistant. 15 minutes is fireproof. It's fireproof, but it still only takes 15 minutes to burn through it. So there's different languages used, and of course the testing regime, the certification regime in aircraft, with it being so safety dependent, the test houses themselves need to be fully accredited, and you'll need to get your testing done by someone that's compliant with NADCAP. So fire tests are, again, many and varied. We talked about tests for non-combustibility. This is really how much organic content is it. So it's a saw plugger material put inside a furnace, and you actually look at weight loss and any sort of fume that might come off it. And you've got a very small percentage that you can get away with for something to be non-combustible or of limited combustibility. Ignitability testing can be anything from a small flame or cigarette to sort of full-scale burners, and fuel load and heat release can be tested in a number of ways. And again, this can be crib tests, it can be cone calorimeter tests. Flame spread is usually done on sort of relatively small panels with sort of angled burners. There's an awful lot of testing here, and I'm looking at the timing. There's a lot of lists of tests in the guide, but actually choosing knowing what your test is going to be is very important to designing your composite or choosing your composite material. So finally, what's going to happen? What are the main challenges that we see going forward? What's new? So we mentioned electrification of transport and mobility. Batteries are becoming much more power dense, and inherently, in some cases, because they contain so much energy, they're inherently more dangerous. They're also going into applications that require lightweight. So, looking at the safety of those battery cases and battery containment is really a growth market, and the standards have not yet quite caught up. So there's relatively few that are agreed. So it's an area where there's room for innovation, I would say. High temperature performance. This is an area where composites are constantly pushing the envelope in terms of the performance areas they can get to. We're always looking for getting lightweight materials into higher and higher temperature environments. So, using some of the additives, using some of the more unusual materials, I think, to tweak composites up into those places is going to be critical. Thermoplastics, again, really good to see them being used more often. They're also buying their way into an awful lot of automotive and aerospace applications. Some very nice high performance thermoplastics that really deal with flame very, very well. So we'll see more of those, and we'll see more of those being tested and attacking different aerospace applications in particular. Getting the fire resistance cleaner and greener is very much a trend. We've already seen that antimony and halogen systems have been sort of targeted from the point of view of the actual chemicals themselves being having health and safety concerns, and what happens to those at the end of life. So if we've got a fire resistant material containing additives, how do we make sure that those additives are safely contained, recycled, and brought back into the materials loop without causing an issue? So all of those things are important, and of course we'll be looking more and more widely for sustainable materials, non-petroleum based, perhaps bio-derived, that have good properties that we can actually use to make our composites more fire resistant. So I'm going to finish there. Questions, please pop them in the chat box or the question Q&A box, and we'll carry on from there. And I'd like to say thank you to National Composite Centre for commissioning the guide we've issued, to Stella and Claire for helping me put the presentation together, and for the reviewers of the guide and contributors, which were very useful when we put that together.
Thank you very much, Nigel. A very interesting and helpful summary. So we've got a number of questions. Just thought it might be worth very briefly mentioning a good news article that I saw this morning, which touched on two of the areas in your last slide there, which was that TRB Lightweight Structures has won a £19 million deal to export electric car battery parts. It says made from organic waste. I think that uses some sort of bio-based resin. So that's very encouraging. So that's for electric battery parts.
Yeah.
So that's really good news. So moving swiftly on to the questions, we have a number of questions here. I'll just go through in the order they are. First one from Composite Braiding. Has layout configuration of laminate proven to have any effect on fire retardants?
If you can, obviously layout configuration is important. So if you have quite often with the layout, you want a resin-rich surface layer to enable you to get flow into your detail and not to have sort of stiffer, chunkier fibre exposed. So you have to be aware that if you are having a resin-rich surface, it can affect fire testing, affect spread of flame, it can affect ignitability. So you can have an imbalance, if you like, through a laminate of your fire performance. And that's where, perhaps you want to consider veils or coatings or in mold coatings to boost that, or perhaps, higher filler content on surfaces. We've also seen with things like where you have sort of quite chunky and sort of mixed layout. So if you've got resins within, if you've got a mixture of high fibre content and low fibre content areas within your piece, then you can get sort of differential burning through a part. If you're doing a burn through, you may find that certain areas that are resin rich may burn faster and give you penetration issues that you don't want. So yes, layout has an effect, but it rather depends on the test, whether it's a surface spread or whether it's a burn through type test.
Okay, thank you. The next question, it's anonymous here. Do you have any case study on improving fire resistance behaviour of bio-based composites? I guess that has a fairly broad range of answers, but if you could briefly summarise.
Yeah, so a lot of the bio-based composites, there's some good things you can treat them with. Some of them are actually not bad themselves. So things like wool, for instance, as a fabric is nice and good starting point for fire resistance. Some of your other sort of natural fibres are actually not too bad in terms of your essential fire performance. You can improve them. So things like ammonium polyphosphate solutions and other solutions are used to treat those fibres or fabrics, and they can give you a boost, quite a significant boost to your fire performance. And there's quite a lot of work being done in universities on some of the nano additives. So if you want to meet a aircraft textiles sort of specification with a natural fibre or fabric, then you can use things like zirconates and whatever. So there are solutions of metal oxides and some additive solutions that you can coat onto or impregnate your fabrics with that can really give you very high level of fire performance. And obviously then you can embed that into a composite with a higher level of performance from your actual fabric content.
And I think there are some resins, bio-based resins, that are quite fire retardant as well as that.
So, yeah, certainly. So we're seeing, I mean, a few of our alcohol, some of the sugar bagasse derived ones, some of the cashew nut shell liquid derived resin components are very useful and have got excellent sort of phenolic type fire resistant characteristics. So choosing a good bio or some content of bio-based resin systems are actually quite good fire resistance ones. So yes, natural solutions are certainly, you know, a possibility.
Thank you. The next one here is about thermoplastic composites, which, as you mentioned, is a growing area. Can a rich fire retardant coating increase fire safety of thermoplastic composites? A lot of solutions in the presentation are very well suited for thermoset polymer resin systems.
So some of the thermoplastics are actually pretty good in fire, that particularly if fluorinated and things like that. So, and a lot of thermoplastics or even some of the thermoset materials are protected by things like a PVDF film or PVC film. So they, you know, some of the ignitability aspects of them quite often are you know, surface protected with a film, which may itself be thermoplastic. When you talk about things like you know, PEEK and PPS, they're actually pretty flame resistant in themselves. So thermoplastics, certainly at the high performance end, needn't necessarily be a problem for fire. They're pretty good to start with. I think where they do struggle is their structural performance. So if they drop below if they get hot, they tend to sag more sort of you know, shall we, melting and softening behaviour is more of an issue. So really, it's a question of whether you're talking about structural failure or actually sort of contribution to fire. So again, it tends to be application and sector specific and test specific, but you know, thermoplastics certainly have their place. It really depends on what the consequences of failure are, if you like, in your fire scenario.
Thank you. I'm just wondering if the person from Composite Braiding there, not sure which one it is, if you have any further comments on that. If you drop me a note in the chat, then I think I can allow you to speak. I haven't tried that before, but I think I can. But I'll move on to the next question for the meantime. This is I think actually I'll go to the last question and then the previous one, because that one could take a while. So Yuri Ganfeld says, we're basalt FRP rebar manufacturers using epoxy resin system, reinforcing agents basalt fibre. What's the best solution for us to increase fire resistance?
Right. Well, basalt's pretty good in fire. It outperforms quite a few of the glass materials. So the basalt itself is not so much an issue. It's going to be what you can do in the matrix. So if you're, and obviously it depends on, if you're doing it rebar, you're wanting to have the maximum fibre content and good wetting and everything else. So epoxies may not, you really got to look at your fire retardant components within your epoxy. So are you talking about, you know, adding extra expense and going to a higher performance epoxy by putting some fire retardant epoxies in there? There are some, you might actually consider some of the, some of the other resin systems. So you might have a look at some of the newer things like fluoride alcohol. You might look at some of the hybrid urethane type chemistries. Some of those can be actually pretty good in fire and perhaps better than epoxies, and possibly even cheaper and perhaps faster processing in a rebar situation. So there's some other options you've got other than epoxy. You may have to compromise a little bit on some of your mechanical performance, but so there you go.
Thank you. So then there's this question from Graham Murray, Grenfell cladding.
Yes.
The inquiry has shown a complete lack of knowledge by the procurement people responsible for the refurbishment before the fire. Question 1, is there any delegate watching from local government? And I was trying to get to the list. I don't have the list ready to hand, and not everybody's got their surname in there, so I'm not quite sure the answer to that. If there is, you could pop.
Grenfell's a challenge because the word composite was used to describe the Grenfell cladding, whereas actually, and yeah, I guess it's from a construction industry point of view, it's a composite. It's a combination of aluminium, painted aluminium, and thermoplastic foam. But it's nothing to do with the FRP composite world as we know it.
So the second part of Graham's question was, what solution would you recommend?
We have a big challenge with the standards authorities in that, because the knee-jerk reaction is to completely specify that we are moved to non-combustible materials, and that seems to be the initial reaction of the regulators to anything above a certain height insist on non-combustible materials. Now that's kind of throwing the baby out with the bathwater in a way. It does seem to me that combination of materials, which they didn't even use a fire retardant foam, with the aluminium, so there was clearly a breach of even the standards that did exist. But actually, sort of the flame tests that are done on foams are kind of inadequate when you're talking about a fire scenario for building claddings. Most foams, and some will tend to shrink away from a flame, and if they don't stay on the flame long enough, they won't necessarily sustain burning. So the simple tests you do on foams don't necessarily reflect the fire scenario. That when you've got a fully developed fire, the foam will melt and drip and contribute fire load to it, and that's what happened there. And it was, because it wasn't even a fire retarded foam, it wasn't going to stop. So some big issues about that, and it's very sad for our industry, if you like, that the word composite is used to describe those panels. And it will be sad if non-combustibility becomes an essential for cladding systems, which will prevent an awful lot of innovative and very useful lighter weight solutions for things like rain cladding and building cladding. So I'm kind of waiting to see where the regulators take this. I'm not particularly optimistic that politics won't sort of dictate that non-combustibilities becomes the way they go. And I think we have a place, and I've certainly tried to influence talking about the success of FRP insulation and cladding systems that are made properly and fitted properly, and how good they can be compared with other materials. But I think we just have to wait and see where the politics takes that, because as you say, it's really not understood very well.
We have technically come to the end of our hour. We have one more question, so if people need to leave, then that's absolutely fine. Nigel, are you okay to stay?
Yes, I'm fine.
A couple more minutes and finish the last question? Yeah. Just one thing on Grenfell, I think some members of Composites UK did contribute to some of the government consultations after that.
Yes.
And I would encourage people to contribute to those kind of consultations, because if we don't shout out and say, actually, non-combustible isn't necessarily the best thing, then we will get stuck without a big market where we could actually provide a useful material. So it's very important to get involved in those standards and regulations issues. And the last question is from John Evans. You mentioned high fibre volume fraction GFRP laminates as having good fire resistance. How does CFRP fare in comparison?
Well, it really depends on your test. So carbon fibre of itself isn't particularly flammable. So if you talk about glass versus carbon, until you get to really, really high temperatures, carbon's going nowhere in most fires. It doesn't tend, unless you get very, very hot. Carbon fibre itself isn't going to burn. So you know, so to some extent, it really, again, depends on your test. If you've got sufficient flame resistant resin systems and sort of low ignitability in a carbon fiber reinforcement, unless you're doing something that's a very, very hot burn through, you should be okay. You'll tend to leave the carbon behind until you get to, sort of temperatures sort of well above sort of 600 and 800 degrees centigrade. It doesn't tend to sort of disappear that quick. Glass being inorganic will last and survive much higher. And glass also has a reflective and a insulative effect itself. So if you're talking about a barrier that's lightweight and perhaps a wall system, and you're talking about glass versus carbon, then glass or basalt will perform better than carbon in terms of preventing flame spread through a barrier. Yeah, I don't know quite where you're taking that question.
I guess it's a more specific application would give a more specific answer, but okay. Thank you very much, Nigel. Thank you to all those who've been listening. Yeah, it's been great. So just to reiterate, you will get a copy of the video and the presentation and of the good practice guide after the event within the next couple of days. So hope to see you all again at another one of our webinars in the future. So are we going to add something, Nigel?
Yeah, I was just to say really, there's an awful lot of information and detail in the good practice guide. In 40 minutes, I can't really do it justice. No. so a lot of the references to standards are there, and I have been following the Grenfell sort of legislative issues. So if people do have questions on specific stuff, I'm very happy to follow up on some of those.
And I think it is quite a theme, at least in the beginning of the guide, of the need for people to work together, the designers and the clients to work together and establish a clear understanding of what's needed in the design, because often there are different terminologies that are very confusing, as you've pointed out, I think, Nigel. So good. Thank you very much, everyone. We hope to see you soon in other webinars.